Hi everybody, today we're going to talk about geometric Brownian motion. So let me write that down. Oof. Geometric Brownian motion. So geometric Brownian motion is a sort of Brownian motion that is more relevant to finance. And so I think we have to discuss what that means. So um, I guess if you think about the price of a stock, you're thinking about it in terms of what percentage is going to increase by. Let's say the price is right now $10, and then it goes up to 12. You think I made a 20% profit. Um, and so what matters here, notice in this scenario, is that it doesn't matter what the actual price of stock is. What matters is the percentage change. So the everything that happened before, its current price, none of that matters. Again, only percentage change. So in other words, this value xt plus s over xt should be independent um, of anything before time t. So, okay. Um, so let's talk about the what geometric Brownian motion is. So geometric Brownian motion, we rated GBM of two parameters mu, this is called drift, and a variance sigma is written according to this formula. So xt is x0, so this is an initial value. X0 is the initial value, multiplied by e to the power of mu minus sigma squared over 2 times t plus sigma wt, where wt is the standard Brownian motion with mean 0 and variance 1, as discussed in the previous lecture. Discussed previously. Okay, so notice that going back to our definition up here, xt plus s over xt is we can. Sorry, I haven't described what xt plus s is. So let's do that. So let's try to calculate this value, xt plus s. This is equal to x0 multiplied by e to the mu minus sigma squared over 2 multiplied by t plus s plus sigma wt. So now let's do a little trick. Let's subtract from here sigma ws. Is that right? Yes, and then add sigma ws. And let's reorder the terms around a little bit. So we end up with x0 e mu minus sigma squared over t multiplied by s plus sigma ws, and then here plus mu minus sigma squared over 2 times t plus sigma wt minus ws. Okay, ws. So notice here that this thing right here is just x of s. So rewriting it, we end up with this e mu minus sigma squared over 2 multiplied by t plus sigma wt plus minus ws. So now let's move the xs underneath. So we end up with xt plus s over xs is e to the mu minus sigma squared over 2 multiplied by t plus sigma multiplied by wt minus ws. And as we discussed about Brownian motion, the difference between two Brownian motions is a normal distribution with mean 0 and standard and variance, the difference between them. So sorry, this shouldn't be t, this should be this should be t plus s. I made a mistake here. T plus s, with a difference between them, so t in this case. Okay. So in other words, this is equal to this is sort of like constantly increasing, but this is again this is proportional to t, and then this is again proportional to t. So this is perfect for us according to the the percentage increase in the stock is basically not dependent at all on any previous value. It is only dependent on t, which is the size of the interval that we're computing over. Okay, so other things that I wanted to talk about. So here's a graph of geometric Brownian motion with different variances, and mu equals 1. So mu here is fixed, and then we have different values of sigma. And so here we have sigma 1.8, sigma 1.6, sigma 0.8. So notice that very high values of sigma, it's possible for this second term to overpower the mu, in which case the Brownian motion eventually goes to 0. Why? Because this whole term here is negative. That's why it goes to 0. However, for low values of sigma, you can see the expected exponential distribution. So I think it's kind of interesting how for these large variances, this geometric Brownian motion goes to 0. Okay. The other thing I wanted to talk about is that this equation comes from this differential equation. So let me write it out. D of xt is equal to mu. Let me just check to make sure that I have it correct. Okay, mu xt dt. Sorry, mu xt dt plus sigma dwt. Sorry, I think there's an xt here as well. Yes, correct. Okay, so yeah, just looking at this, sort of how do we understand this? Well, we have this random variable xt that is increasing according to the drift. So by mu, it's increasing multiplicatively by mu and then multiplied by dt. And at the same time, it's affected by this random Brownian motion that has a stronger effect depending on how big xt, which is exactly what we expect. Again, this should be like multiplicative. And then the sigma is the variance sort of parameter. So that's how we could understand this situation. Okay, so let's calculate the expectation of at time t of xt plus s. Why are we doing this? I think we just want to understand how much this xt plus s has grown given, like how much we expect xt plus s to grow given that we are at time t. So to write out the equation, so inside of here we have x 0. Oh yeah, I need to discuss one other thing after this. E of mu minus sigma squared over 2 multiplied by t plus s plus sigma wt plus s. I think as we discussed, this is equal to, I should have written this originally like this, of xt e to the mu minus sigma squared over 2 times s plus mu this t plus s minus wt, like so. Okay. So notice if we are aware of all information up to time t, then this xt just comes out. And so we just end up with xt here, and then e to the, expectation, let me just check. Squared. Yes, so I mean, obviously I forgot to mention this s is not a random variable, right? It's just a constant. So we can take this out of the equation as well, and we have e to the mu minus sigma squared over 2 multiplied by s, and the only thing we have left to calculate the expectation of at time t is this thing, e to the sigma wt plus s minus wt. However, as we have noted, this is normally distributed, and moreover, This is, yeah, so this is normally distributed, and again, where have we seen this before? This is the moment generating function of this WT plus S. So I mean, this looks like a moment generating function, so we know how to calculate this. This is in fact e to the let me just check, e to the, I mean, it's normal. Again, this is normal. This is the normal distribution with mu 0 and variance S. And so we end up with mu squared over 2S. So as you know, there's like the expectation of e to the Sx is equal to, I mean, technically a plus bx, let's just say that, where x is a random variable, is equal to, as described, let me see, it's equal to e to the a s, e to the a s plus 1/2 b squared x, I think is correct. B squared, sorry, s squared. Okay. Is there a z in here? Oh yeah, that's right. So where obviously x is the is a normal is a normal with, oh, this isn't even true. Oh no, you're right. It's a plus bx. That's right. So if x is a, yeah, where x ax, yeah, where a plus bx is the normal. A plus bx is the normal distribution with mean A and variance B. Okay. So what did we learn from all of this? Yeah, and so this right here, this result here, it cancels out with this, and we just end up with e to the mu s multiplied by xt. Okay, so what does this mean? This means that on average, this random variable has increased by this factor, right? This multiplication factor here, e to the mu s. So that's like a rate of growth of the stock. If we're going to represent a stock by a geometric Brownian motion, this is how much it has grown. Okay, great. So let's talk about some, oh yeah, I wanted to talk about how do we simulate geometric Brownian motion. That was the thing that I was forgetting. So let's just say we have a timeline here. We start at time 0, and we have several points which we want to plot on a graph. T1, T2, T3, T4. Again, we have this formula for geometric Brownian motion, which is x of t plus s is equal to x of s, e to the mu minus sigma squared over 2 times t plus sigma wt plus s minus ws. So if we simulate the first T1 just normally with this formula, then we can, if we know this value already, we can get the value of x of T2 just by using this formula, right? Using s T1, right? Because we know what this value is, and taking again, or like this whole thing is normally distributed, right? So we can find this difference normally distributed, and again, since the increments are like they're random, they're not dependent on each other, then we can do this sort of situation. Okay, great. Okay, so some properties of geometric Brownian motion. I think we already went over this, but xt plus s over xt, or generally, if we pick increments, tn divided by xtn minus 1, all the way to x2 over x1, xt2 over x1. All of these are independent, as described by this formula, right? This is completely independent. This is normally distributed again, and this is just a function of t, so the random variables, they have no effect on each other, which is great. Okay, 2, obviously xt is continuous given that all of its constituent parts are continuous. Finally, if we take the log of this distribution, xt plus s over xt, this is normally distributed with, I think it's like mu, let me check, with mu minus sigma squared over 2s. And so this is a log normal distribution as we described in a previous lecture, mu squared s. So where does this come from? We take the natural logarithm of both sides, this e goes away, and we end up with this multiplied by t plus this normal distribution factor. So on the mean of this normal distribution is equal to this, and then the standard deviation is this sigma squared s. Because this geometric Brownian motion, again, the variance increases as time increases, so that's why it's sigma squared s. Okay, great. I think as a final point, again, this we can model stock prices using geometric Brownian motion, given our whole discussion so far, and this is the underlying model for Black-Scholes. So thank you so much. I'll see you next time.